Hi, I'm Vaidehi. I'm so excited because today I get to tell you all about the rainbow. And hexadecimals, of course. You might be familiar with the number 256 and its unique relationship to binary and also bytes. But it turns out 256 doesn't just have to do with binary, it has to do with another number system as well. Hexadecimals, or base 16. Base 16 is a really special number system when it comes to computing. As we might know, base 2, or binary, involves just 2 digits, and base 10 involves 10 digits. By proxy, we can assume that base 16 involves 16 digits. But where do you get 16 digits from? Well, we know that we can use the digits 0 through 9, as I have labeled right here. But that's just 10 digits. Where do we come up with the extra 6? Well, if you think about it, we decide and attribute the meaning to numbers. So why don't we just come up with other things to symbolize numbers too? And that's actually exactly what you do when it comes to base 16. In base 16, we use A, B, C, D, E, and F to symbolize the digits 10 through 15. Remember, we're starting at 0. And in this case, we need to think about these letters not as letters, but as numbers. And then if we count all of our digits up, we actually have 16 digits now, which allows us to count in a base 16 number system. But how do you actually use 16 digits to count? I think it might make more sense with an example, so let's take a quick look. Here we have the number 205. Remember that 205 is how we read it in base 10. So this is just the number 205 represented in base 10. And that's what we've highlighted right here. But we can represent the same number, not just in base 10, but also in base 2, or binary. In binary, 205 is represented as 11001101. Okay, that's fine, but now let's go to base 16. We haven't counted with base 16 before, so let's think about how we'd represent that. Well, in base 16, remember that we're counting beyond the digits of 0 through 9. We're using letters. So, in base 16, the number 205 would be represented as CD, which is kind of interesting. What else is interesting is if we look at the progression from one base to the next, we'll notice an interesting pattern. If we look at each base, starting from base 2, progressively working our way up to base 16, we'll notice that the higher the base, the fewer digits we actually need in order to represent the same number. We'll start to see how that's really powerful. For example, with 205, we needed 8 digits to represent this number in binary. But we only need 2 digits in base 16 to represent the same thing. Based on this information, we can start to see how base 16 can actually be pretty powerful and how we can leverage it. Because we now know that we can use 2 consecutive base 16 digits, for example, C and D to represent 205, in order to replace all the binary digits that we used previously when we wrote it in base 2. In other words, 2 consecutive hexadecimals can be used to represent 8 bits of information. We're still compacting the same amount of information, but we're using far less space, far fewer digits to do so. Hexadecimals are all around us, and one of the most interesting places that they show up is in colors. Computers and most devices in general have pixels in them that use the additive color theory model. The additive color theory basically tells a pixel how much red, green, and blue to add in order to create a brand new color. Let's take a look at a quick example of how this works. If you've ever worked with CSS or style sheets in general using colors, then you probably know that there are different ways of representing colors. And those representations actually exhibit the additive color theory model in action. For example, if you wanted to represent the color black, you could represent it using a hex code 000000, or you could also say RGB 000. This is basically saying to use no red, no green, or no blue in order to create the absence of color, which is black. On the flip side, with white, we do the opposite. We use a hex code that uses the highest level of red, green, and blue. When we add all these colors together, we get a full concentration of all colors, which gives us white. You might notice that there are two different ways of representing black and two different ways of writing white, but they're both equivalent and result in the same color. Well, it turns out that these two ways of representing color have a unique relationship with one another, and they have to do with hexadecimals. So let's take a look at the relationship between these two representations and how hexes fit into the mix. We can represent colors in two different ways. We can use the hex value, for example, looking at this one color, EC152E, or we can represent it in the equivalent RGB format, 236/2146. We know that the RGB value tells us how much red, green, and blue to add. For example, we used a lot of red here, some green, and some blue. But how does that connect to this hex value? What's the relationship there? And especially, how do they work if they're equivalent and resulting in the same color? Let's take a closer look at the relationship between these two representations. Each of these decimal base 10 numbers also can be represented as 8 digits in binary. And we also know that 8 binary digits are equivalent to 2 consecutive hexadecimal digits. So, the number 236 could also be represented by 2 consecutive hexadecimal digits. What's interesting is if we convert the number 236 into hexadecimal, we'll notice that the hex representation of 236 is EC. So you might be able to guess what we can do with green and blue here too. The number 15 in hex, when converted into base 10, is actually 21. And the number 2E, when converted into base 10, is the number 46. So these 3 pairs of hexadecimal digits are actually the hex representation of how much red, green, and blue to add, which is pretty cool, especially because it might not be obvious at first glance, but they're really doing the same thing and representing the same color. Another interesting connection between the hex model and the RGB model is how much space they both take up. We'll remember that 2 consecutive hex digits is the same as 1 byte of information. 2 hex digits is equivalent to 8 bits. By extension, if we only have 1 pair of hexadecimals to represent red and green and blue, that means each pair can only take up 1 byte of storage and data. A single hex code contains 1 color value, but it only takes up 3 bytes or 24 bits of information. So, if you've ever wondered why an RGB color value can only ever accept a range between 0 and 255, the reason is 1 color has to fit inside a single hex pair value. For each byte, there are 256 permutations, which means for 3 bytes, there are actually over 16 million colors that can be represented within the color spectrum in just one hex code. A single pair of hex digits and their relationship to 256 makes hexadecimals super powerful to use. And they show up not just in colors, but also in hex speak and also in IP addresses. The unique relationship between hexadecimals, binary, and a single byte makes them very easy for developers to use, and they show up as abstractions all over the place. If you want to learn more about hexadecimals, head over to Dev2 and follow me at Vaidehi Joshi. You'll also get to stay up to date on all my latest videos. Thanks for watching.
Thanks to Heroku for sponsoring BaseCS. I'm Ben, one of the founders of Dev, and I want to give a shout out to Heroku, the platform that's allowed us to scale from 0 to millions of monthly visitors since we started this venture a few years ago. We rely on Heroku's managed Postgres alongside the rest of their infrastructure to ensure reliability and flexibility as we scale. If you're looking to scale a complex web app without all the chaos, please check out Heroku. Thanks a lot.